two notations that represent the orthogonal projection of a vector y onto a vector space W. So one of them is y hat, and the other one is the projection of y onto W. So I'm going to draw a picture of what this is. So last class we did a projection of a vector onto a line, and it was dropping a perpendicular from your vector onto the line, right? So quick picture of what we did here. This was the vector y, and then we had this line, which was the span of some vector u, and we dropped a perpendicular down to here, and this new point was y hat, or the projection of y onto W, where W is the line. If we have a whole space, a multi-dimensional space, it's not just a line. So you've got a span, this is W now. It's a plane. And if y is up here, then the projection of y onto W, or y hat, is dropping a perpendicular down to the plane. So this would be y hat. So y hat is also the point in W, right? So in this case, W is just a one-dimensional line. In this picture I drew, it's a two-dimensional plane. But this definition expands to higher dimensions. I just can't draw them for you. But y hat is always the point in W that's closest to y. Right? So if you drop a perpendicular down to the two-dimensional plane W, that is the closest point in W you can get to y. And the same with the line. Y hat is the closest point to y that lives on W. Okay, so we'll talk about a little bit more about this stuff when we go over the lecture for 6.3. But we left off last class just finishing the 6.2 lecture. So I'm going to have you spend, I don't know, 30 minutes or so on the finishing 6.2 activities, and then we'll come back and do the lecture for 6.3. Okay, so in our daily quiz, I talked about what we're going to do in 6.3, right? So in 6.2, we found the orthogonal projection for a vector y onto a line that goes through the origin. So y hat is the vector on that line, and then z is the orthogonal component of y. So today what we're going to do is we're going to be projecting onto a whole plane. So instead of our subspace W being just a line, now it's going to be two-dimensional or more, right? So I'm going to project y onto a plane W, meaning find the closest point in W to the point y. Drop a perpendicular from y into the plane W, and we'll find y hat and z. Y hat being a vector that lives in W, z being a vector orthogonal to W. Okay, so for a line, y hat was in W, meaning it was on the line, and z was the orthogonal component of y. All right, so some pictures to describe what we're doing when we're in when we're in two dimensions. So I want to find y projected onto W, the projection of y onto W. It's known as y hat. It's basically drop a perpendicular to the plane. And then the way we find y hat is this formula that looks just like the way we found it for a line, right? Except it's got two, you do it twice and add them together now. So U1 and U2 have to be an orthogonal basis for W in order to use this formula. So the way it works is if you want to find the projection of y onto the space W, W is defined by U1 and U2 that are orthogonal to each other, and they span W. All right, so what you do is you take the orthogonal projection of y onto U1 and U2. So you find these two orthogonal projections, which is what we did in 6.2. And then when you add them together, right, if you add this vector and this vector, you use that parallelogram rule for adding vectors, and you land at the y hat that you're looking for. So that's what's happening graphically. You're finding the two projections onto U1 and onto U2, and then you add them together, and you get the projection y hat. So let's do an example. So I have y, u1, and u2. W is the span of u1 and u2. You can only use the formulas that I just showed you if u1 and u2 is an orthogonal set, which means I have to check that their dot product is 0. So 1, 3, 0, dot product with -3, 1, 2 is -3 plus 3 plus 0, which is 0, check. So because they're an orthogonal basis, u1 and u2 form an orthogonal basis for w, I can use my formula to calculate y hat, which is on the next page. The orthogonal projection of y onto w, also known as y hat. So the formula is y, when w was just a line, this was y dot u over u dot u times u. But since w is a two-dimensional space now, we know it's two-dimensional because there were two vectors in the basis, right? So it's two-dimensional. That I have to do this twice, once for u1, once for each vector in the basis. So this is going to be y plus y dot u2 over u2 dot u2 times u2. Okay, so y is 2, 2, 3. u1 is 1, 3, 0 over 1, 3, 0 dotted with 1, 3, 0 times 1, 3, 0. Oh, this? That's just the fraction bar, didn't finish. Okay, and then y is 2, 2, 3 dotted with u2, which is -3, 1, 2 over u2 dot u2 times u2. Okay, so when I take the dot product here, I have 2 plus 6 plus 0, so that is 8. And then the dot product in the denominator, I get 1 plus 9 plus 0 is 10 times 1, 3, 0 plus dot product in the numerator over here is -6 plus 2 plus 6 is 2. And then in my denominator, I have 9 plus 1 plus 4 is 14. -3, 1, 2. Almost done. Okay, so 8/10 times 1, I'm going to reduce as I do this. 8/10 times 3 is 12/5 and 0 plus -3/7. 1/7 times 1 is 1/7, and 1/7 times 2 is 2/7. Okay, so then I'm going to add these two vectors together. You need to get a common denominator, or just like let your calculator do that. 13 over 35, 89 over 35, and 2/7. So that's my y hat. That is the projection of y onto space W, which is the span of u1 and u2. Now, I didn't ask you to, but I could ask you to write y as the sum of two vectors, one in W and one orthogonal to W. I just found the one in W, right? So I could write my y as y hat plus z. Y hat is in the space W, that's the one I found. And this one is in W perp or in the orthogonal to W. So Y was 223. I want to write that as Y hat. I already found 13 over 35, 89 over 35, and 2/7 plus another vector. So you just have to figure out 13 over 35 plus what gives you 2. This is the subtraction part. Like to find the z, you just do y minus y hat because this is what you're trying to do. So 2 is 70 over 35. So 70 minus 13 would be 57. So then 70 over 35 minus 89 over 35 would be negative 19 over 35. And 3 is 21/7. So 21/7 minus 2/7 is 19/7. So this is my y hat, this is my z. Y hat is in the vector space W. Z is perpendicular to W. You can double check. If you take the dot product of these two vectors, they should be orthogonal. So that's just a quick way to like check your work. If you came up with your answer and you're like, okay, they do add up to y, you can dot product to check that they're orthogonal, and then you'll know that you did everything right. All right, so that's it for the 6-3 lecture.